That's in. Shoot. Okay. Take good notes for your friends. The one day I don't set up the video camera and I forget to hit record. All right. Let's look at this equation for a second. What this equation is saying is that if I take a small time step, delta t, I can say how much charge has been deposited on the capacitor plate. If I know the time, if I give a time interval, I can say how much charge has been deposited on the capacitor plate. And incidentally, notice the amount of charge that's deposited on the capacitor plate also depends on the amount of charge already on the capacitor plate. So the amount that I put on the plate depends on how much is already there. Now I'll have to go and look at a biology textbook, but this will be a heuristic argument. You know that, for example, population growth. The growth of a population next year depends on the amount of population you have this year, right? The number of rabbits that I get next year depends on the number of rabbits I have this year, for example. You're probably familiar with the logistical equation or population growth equation. You end up with those e to the yada, yada, yada. And then you say, well, wait a minute, the population shouldn't explode. You say, yes, you have to add in predators and other things and food scarcity and yada, yada, yada. But that's where the E is coming in. Any time where you get next year depends on how much you have this year, you're going to end up with some sort of exponential, E to some value. Same thing, virus growth. You know, if you wanted to look at the spread of COVID-19 in the early stages, it was probably exponential for a while, E to the time. And the reason for it is because new infections depend on how many people are currently infected. And then before you put in things like masks and social distancing, that's unabated. So it's just an exponential climb. That's how you can also, if you're a policy advisor, for example, that's one way you can tell, are we having an effect? How much is this thing deviating from a pure exponential growth? Well, that means that some of the policies you're putting in place are actually starting to change the shape of the curve. Anyway, sorry, for those of you familiar with the vernacular, that's a differential equation. So if you've had calculus, there's a faster way to do this just straight off with calculus, right here. You do not need to know that. I'm not saying that to scare you. I'm just saying that you could do it this way as well. Okay, good. So now we have an expression that tells us how much charge is deposited on the capacitor plate based on how much charge we currently have on the plate. We will now use that equation to force the computer to show us that we should get these exponentials. Okay? So I need to show you how do we do the computer to do that. Okay. And you said you were familiar with Excel. Let's go to Excel. Okay. Boom, Excel. There we go. Okay, let me see if I can blow this up for you just a little bit. Can I blow this up? Blow up, blow up, blow up, blow up, blow up. There we go. Okay. Now, unfortunately, there are some things that I have to tell the computer. For example, I start off with the circuit. I need to specify what the battery is, what the resistor is, what the capacitor is. I have to tell the computer that initially. So usually how I set something up like this, I'm going to call this VBAT. I'll call this the resistor. I'll call this the capacitor. Okay. And what do you want to put for the battery? What value? Okay, you want 12? Okay. Resistor, yeah, what do you want for the resistor value? I'm sorry? 8? Okay, if you want 8, I am not going to give you a choice. I'm going to call this, let's call this something like 125 microfarads. I think that'll be okay. 8, let's call it 125 millifarads, which is a reasonable value. I said, so I have 125 millifarads. I'm cheating. You said 8, and I said, okay, 8's good. Thank you for not picking a prime number, because 8 I can do in my head. Good so far? These are what's called the initial parameters. The nice thing is that if I do this in terms of the initial parameters, then everything else will change later. What do I mean by that? Well, let's see here. The other thing that I need to do is I need to specify a time interval. That equation that we had written down requires us to think about how far into the future we step in time. Now, if you're doing something like population growth, usually you do something like a year, right? Today is year 0, next year, year 1, how much does the population change? How much does it change the next year? How much does it change the next year? Okay? Or if you're thinking about your bank statements, okay, they can't compute interest on your bank statements every month, usually. So if you have money in your savings account, you'll get some dividend from the bank every first of the month, which gives you slightly less money. If they compounded it continuously, you'd get a little bit more money. Curse the big banks. Okay, so here I need to specify how big my time step do I want. Okay? I'm going to do it something like 100th of a second. I don't know if that'll be sufficient or not, but what I'm going to call this is delta t. I need to tell it how far into the future do I want it to project. Do I want it to go 1 year, 2 years, 3 years? No, I want it to go 100th of a second. So do this calculation every 100th of a second. Okay, I think that's all we need. I think. Just for sake of argument, I'm going to do a couple of extra things in here. I'm going to give it the initial charge of the capacitor. So I'll call this Q cap. Let me put it in A4 just to keep it all together. I'll call this Q cap. So the initial charge on the capacitor, let's just say it's uncharged. Now again, if we wanted to look at the behavior, we could actually change that and see what happens later. So I'll call it Q cap. Yeah, okay, good. Now for the fun stuff. How are we going to tell the computer to do this? Okay. I'm going to call a column time. I'm thinking about elapsed time. So I'm going to start at 0, and then I am going to, let's see, this is C. Are you guys familiar with cell referencing? So if I put equals D2, what it says is take the value that's stored in cell D2. What I'm going to do is add to that the value of my time step, which is at B5. Is that okay so far? Now here's the other tricky thing. I put B5 in here. I'm going to put dollar signs around it. I'm going to put $B, $5. Why is that? If I don't have that dollar sign in, you notice this one says B5, but now if I click and drag, which is the thing I want to do, you'll notice it will never change. Okay. Why is that? Notice now, instead of D3 plus my time step, it's D3 plus B6. When I click and drag, Excel automatically updates going down. I don't want it to do that. Are you familiar with the click and drag? Excel is a really fancy calculator. That's all that's going on here. So here's what we'll do instead. If I put a dollar sign in front of the 5, what that means is anytime I click and drag down a column, it will not change the 5. So this is a way of telling Excel don't change the cell reference to B5. So now if I click and drag, if I take that corner and I click and drag down, you'll see it increments in 1/100th of a second. What it's doing is taking the previous value, adding the value of B5 to it, and then keeps going. Yay? Okay. Okay. Next up, I need the charge on the capacitor. And at time equals 0, this is just the value that I've typed into B4. Said, hey, let's call the capacitor charge 0. I'm just going to set that up as my initial condition. Okay? The next step is I need to know how my charge changes. And here's the big one. Here's where we have to use that equation that we just wrote out. And I want to know, how much does my charge change? Well, we said that it is the battery potential. Let me put this in quotes. We said it was the battery potential, $1, divided by the resistance, which I believe, let's see, $2. Again, I'm putting those dollar signs in because I want to click and drag eventually, and I want to keep that reference the same. And then what do we have in there? We had minus the charge of the capacitor. That one I have stored in E2, divided by the resistor value, $2, times the capacitor value, which is what, $3. Is that what you had on the paper? You had battery divided by resistance minus capacitor charge divided by resistance times capacitance. So I'm just programming in what we had on the piece of paper. The last thing I need to do, multiply by my time interval. I had a delta t out there. So my time interval, I decided the time interval be $5. Is that okay? That's the delta t that I had in front. I said, let's do this every 1/10 of a second. So based on a 12-volt battery, an 8-ohm resistor, a 125 millifarad capacitor, if I throw the switch a 1/100th of a second later, the charge on the capacitor is 0.015 coulombs.
Where did E2 come from?
Where'd the, I'm sorry?
E2.
E2 is the initial charge of the capacitor. So the charge that gets put on the capacitor depends on how much charge is already there. So if it's fully charged, no more charge gets put on. But that's where the E2 is just representing the charge that's currently on the capacitor. Yes?
The only thing that's gonna follow the drag and push is the Q cap column.
Good. Yeah. You notice the only thing, since I put all these dollar signs in, when I click and drag down, yes, the only thing that changes, and if we look at that equation that we wrote down, the only thing that changes in that equation is how much charge is on the capacitor. As time progresses, the resistance stays the same, the battery stays the same, everything stays the same except for the charge on the capacitor.
So you only multiply by how much the time is changing the actual.
Correct. Yeah, we want to multiply by the time step, not the accumulated time. And you do that with population as well, right? You don't if I want to know the population in year 10, I first go through years 1 through 9. And then I get year 10. I don't jump straight to I don't use population at year 0 and then use 10 as the next step. Yeah, you do it. So yes, that time interval is how far do I increment the time. Now, for completeness, I'll put Q cap final here, just to remind myself. If I started off with 0 charge, and now I can add to it how much it changed by, that tells me what the final charge on the capacitor is. I'm just taking how much I started with plus how much it changed by to get my final.
What is? Sorry.
No.
So I thought you were calculating Q cap final on the
Yeah, sorry, let me call this Q cap. I'll call this Q cap initial. So how much I started off with in year 0 is Q cap initial. Q cap final is how much did I have after that the time.
Would that be it? Sorry. 0.14 or?
This value, the 0, would be the instant I close it. And this would be 100th of a second later.
So it's Q cap F B X also the same thing as E3.
Would Q cap F be the same thing as E3? Yes. In fact, that's the next step. Because if I understand the question correctly, after 100th of a second, I now have my final charge on the capacitor. That becomes the new initial charge for my next step. Is that what you meant? Yeah. Yeah. I think you jumped ahead, which is good. You see where I'm going, I think. What I'm going to do is the new initial charge will be the old final charge. In other words, after I go 100th of a second, okay, that's my final charge. Now that becomes my new initial charge for the next time step. Again, going to population growth, after year 1, the population of year 1 becomes the new starting population to go to year 2. And the population for year 2 becomes the new starting point for year 3, et cetera, et cetera. Now, luckily for us, we are now done. Because of how I set this up, I can click and drag, and now we see that after 200ths of a second, you notice that the delta Q has decreased ever so slightly. Because I already have charge on my capacitor, the additional charge I put on is slightly less. And so the final charge of the capacitor is increased. And now here comes the fun spot. We are now forcing the computer to do all of these tiny little calculations over and over and over and over and over again. So that at 14 milliseconds, no, excuse me, 140 milliseconds. Okay, you can read it. 0.14, this is how much charge is now on the capacitor. And now we run like Charlie Brown. We have set everything up, so now the only thing that we have to do is be patient enough. Right? We can just click and drag, and how far do you want to go? 5 seconds? Let's go 5 seconds to the future. So now we have just gone 5 seconds into the future. We have plotted out the charge on the capacitor 5 seconds after the switch is closed. Notice you can already see 0.148, 0.148, 1.148, 0.148, blah, 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 0.149. You can see that it's a lot smaller of a change. And that's what I mean by, hey, we're going to force the computer to do it for us. And again, this is why it's called numerical simulation. I'm forcing the computer to do a bunch of tiny calculations to get me the final answer. So it's not doing it in terms of variables like you know how to do. It's doing it numerically, little numbers, plugging in. You ready for it? Let's get the coup de grace and then we'll call it quits for today. All right? Let's go ahead. What I want to do is let's go ahead and plot time. Let's plot the final capacitor, the charge on the capacitor versus time. Now I know that that's not the current. I'll have to change it for the current so we can see that relationship as well. But let's go ahead and scatter plot this sucker. Insert. Here we go. And hopefully everything works out. You notice that as this switch is closed, the capacitor starts charging up rapidly and eventually becomes asymptotic. This is the charge. You know that as the charge becomes asymptotic, as it hits a maximum value, what should the current be doing? It goes to zero. Okay? So here's the charge on the capacitor. And in fact, I think I can get the current as well. Right, there's the charge on the capacitor. The current is related to delta Q. So let's plot time and delta Q, and let me insert this. Now this won't have the right scaling on the vertical axis, but you can still see the shape. Okay? You get that exponential decay. Let me show you it's exponential, and then I'll definitely call it quits. You say, well, great, how do you know this is exponential? Let's go ahead and put a trend line in. You familiar with trend lines? Let's put a trend line in. And I'm going to call it exponential. And while we're at it, let's display the equation on the chart, and I'll display the r squared. And let me blow that up for you, because Excel, there. Now it's overwhelming. There. Okay. You notice r squared? 1. What does that mean?
Very precise.
It's very precise. This is a very accurate fit. Yes, I have to look at the residual plots, but the residual plots are going to be perfectly random. Okay. This is perfectly precise. Okay. Notice it's an exponential, e to the negative. And what's the time constant here? According to this figure, what does it say the time constant is? One. Right? Incidentally, I said thank you, Cassie, for picking 8. Because I can do 8 in my head. I purposely chose a capacitance that was 1/8 the resistance. Right? 1/8 is 0.125. So Cassie picked 8. I said, okay, I'll use 0.125 as my capacitance so that my time constant ends up being 1. Yeah. Boom, there you go. That's where the equation comes from. Also notice you could check, but if you take the, this is not scaled properly, but if you take the battery potential and divide by the resistance, you're going to get something like 0.15, if I recall correctly. Double check that, or 1.5, excuse me, 12 divided by 8 is 1.5. So the reason the decimal point is off is because I forgot to divide by the time interval. I'm plotting the change in current, I'm plotting the change in charge, not the current. I'll pick up there, I'll finish up some ideas, but that'll give you a sense of what's going on. Hey, thanks for your attention, I'll see you Friday.